there's a few people I haven't seen proposals from, so please make sure you get those to me as soon as possible so we can get your feedback and get things squared away in the next few weeks. No more questions? All right, cool. So we've been spending a few weeks talking a lot about what I would call maybe tabular data. This is where we have a bunch of more or less independent data points, which you can think of as kind of rows of a table, right? And we're looking at doing analysis of those, right? We sometimes looked at relationships between rows, but really more what we were looking at was relationships between whole columns. So we looked at like correlations, stuff like that. It wasn't really a relationship between two data points, it was between like the columns of all the data points at the same time. So for the next few lectures, we're going to look at graph data, where we are explicitly looking at relationships between pairs of data points at a time. And so we'll look at what some of the things we might be interested in, what we can compute, and that kind of stuff. So, how much time did you spend looking at graphs in last fall?
Oh,
The data structure, the you do any graph search algorithms, anything like that?
I don't remember.
Talked about Dexter's algorithm.
There was an option for Dexter's assignment.
Okay. Yeah. Well, cool. So we'll go through a lot of that stuff. All right. So just to refresh, graph is a set of edges and vertices. And these can model all sorts of stuff. So some examples you might see in the real world that we'll look at. We might have our vertices be web pages and the edges be hyperlinks. We could have our vertices be businesses or consumers, or I guess like bank accounts, and the edges might be transactions between them. The vertices could be cities, the edges could be airplane flights. So those are all examples of graphs that could have all sorts of loops and sort of arbitrary connections. We can also restrict ourselves to trees, where we have hierarchical relationships. So an example of that, we've looked at file systems, but also could be the org chart for a company. Might be a tree. I guess there might be some weird stuff going on if people are in multiple positions or something. But generally, like our department, we have a director and then faculty members below that and whatever. So tree structure there. Family tree, is that a real tree? Does it meet the computer science definition of a tree? No, not at all, actually. So, right, I have two parents. I can't do that in a tree. So, family trees are actually graphs, especially if you have edges for marriage and stuff like that. There's going to be cycles in there and all sorts of crazy stuff. So family tree, not really a tree, more of a graph. But these are, I think you can imagine examples where we might have graph-like data. And so today we're going to look at some basic analysis we can do on those graphs. So maybe before that, let's talk a little bit about how we store graph data. kind of a couple ways we might think about it. So let's say I have, graph of airplane routes or something. How would you go about storing a data set like that?
When you say storage, do you mean the data structure? Or
Yeah, like what data structures would I assume it all fits in memory? Any thoughts? Yeah, maybe lots of pointers. Pointers to what? How do we use pointers? So what, like?
Object is a collection of objects.
So when you say object, you mean a node? Okay. So yeah, one thing I do is I could have like a node. And then I have, I have a vector of node pointers, which are my neighbors. And so for each edge that's connected to this node, right, I store a pointer to the node that it connects to. If I have, how does this work for directed versus undirected graphs? Is this more kind of suited to one than the other?
Directed, but you could definitely make it undirected.
Yeah, this is kind of a directed thing, right? Because I'm pointing from this node to another node. So it's kind of a directed graph thing. If I had an undirected graph, what would I probably want to do?
Always make sure that the pointer is always the pointer.
So if I have an undirected graph, right, I'm just going to store 2 pointers for each edge. Okay. So this is one way. This would be called like an adjacency list representation. We're just kind of explicitly storing a list of the connections. This is kind of a node-centric thing, right? We're doing this per node. Another way we could think about doing this is using an adjacency matrix. So the idea there is I have a big table of all possible edges. And if there's no edge between a pair of nodes, there's a 0 in my matrix. And if there is an edge, then there's something non-zero. So it could just be a 1, right? If it's like, if my edges are unweighted and it's just, is there an edge there or not? I put a 1. Maybe the edges are weight, so maybe it depends on the distance between the nodes or the cost of a plane ticket or whatever else. So in the adjacency matrix, maybe it looks something like this, where each one of these 1s is an edge in the graph. Yeah, does this work better for directed or undirected graphs? So as I've drawn it here, so maybe your first question, is the adjacency matrix that I put in here for an undirected graph? So how could you tell? How could you tell if it?
When you have directionality, like A to B versus B to A, you can have half the size if you were just going to do it undirected.
Yeah, so in this graph I've drawn, I have an edge from, let's say, A to B, but not one from B to A. So as I've drawn it here, this is, I would say, probably a directed graph. If I have an undirected graph, can I be clever in how I do this? If I have a directed graph, this whole area is just duplicated information because I can get whatever I need from down here. So I can actually store half the amount of data if I have a directed graph. Right. So depending on what analysis I want to do, one of these may be more useful than the other. Depending on how I store it, well, which one of these do you think would be easier to add nodes to dynamically if we needed to?
The list, because you don't have to resize.
Yeah, probably the list because I don't want to resize my matrix. So if my graph is going to change a lot, maybe the list is a better representation. We'll see that some operations, the matrix is like a really nice way of storing data for those operations. If there's a lot of zeros in here, right? If there's pretty low connectivity, then it's kind of a bunch of wasted space here to store a bunch of zeros. So actually, there's ways of compressing a matrix like that. So let's say a row here is like I have 1 million columns, and I have like 5 non-zero entries in there. Right? I don't really want to store 1 million zeros. So what could I do to store that information in a smaller way? I have just, there's 5 out of 1 million entries in this row are non-zero. So how could I avoid storing 1 million zeros? Compress it, specifically how? Like how could you? Like run it through zip? It would probably work, but we don't have to be quite as general purpose as that.
Whatever the name for it, but basically like pattern matching. So if you have a bunch of repeating zeros, like it's represented with like a couple bits of information.
Could do that. We know a lot about the specific problem we're dealing with here, so maybe what is a solution very specific to this problem. Right, I have a few non-zero entries out of a whole bunch, right? How can I store that information efficiently? I don't have to store all the zeros. What is it that I have to store? I have to store the non-zeros. Not just the values, but also what? I have to store the locations, right? So I can store, for my huge row here, I'll just say, well, at entry 1, I have a 0.5. At entry 10,000, I have a 2.3. And I only need to store like the location and the value where I have one. This actually looks pretty similar to this. When I store my matrix in a compressed way, it actually looks kind of a lot like this adjacency list representation, but it's still kind of more in the matrix form. So this is how we might store our graph data so that we can work with it. And so now we'll talk about what are some of the operations we might want to perform. We'll talk about some things that are kind of topological that are related to the sort of shape and connectedness of things. We'll talk about some things that are kind of local to a node or a small neighborhood. Because these are all kind of analyses maybe we might want to do. So the first one we'll talk about is it's called connected components. So based on the name, you can probably guess what connected components are. I want to take a stab.
Subsection connected.
It's a subsection of the graph where you can basically reach all the other nodes in that component from each node. This makes more sense for undirected graphs. Right? If I have a directed graph, right, I can have edges between all the nodes, an edge between, one node and all the others or whatever. But if the direction is wrong, I can't actually necessarily reach the nodes from one another. So if we think of the web page example, right? If I have some weird website that nobody knows about, I can have a link to Google. Right? I'm kind of connected to Google, but I'm not really reachable from anywhere else. So for a connected component, in an undirected graph, it's a subset of the graph where all vertices are reachable by all other vertices. And this doesn't mean they have to be connected through a single edge, but I have to be able to go through a sequence of edges to get there. Okay. So in terms of connected components, we're often interested in how many there are. Right? So for a lot of applications, we expect there to be one connected component. Everything should somehow be connected, and if it's not, then that's weird or alarming. Right? So imagine we're dealing with flights or something. So maybe if there were no transatlantic flights, you would have a European connected component and a North American connected component, and there's no way to get from one to the other. Right? That would be an interesting choice by the airline industry. So that's a topological property of the graph. Sort of how many distinct subgroups are there in the graph? For a directed graph, the idea of a connected component is a little trickier. So even if there are, so one thing you do is pretend that we have an undirected graph. So take all the edges, pretend they're two-way, and see if we have connected components. Doesn't tell you quite as much. Right? So the stronger thing would be to apply the same property to a directed graph. Okay? And now this is kind of harder to fulfill, right? Because we have to make sure that the edges go, we have arrows pointing into all the nodes, basically. Okay? And if we have a directed graph and this property holds, this is called a strongly connected component. Okay. So same property, but now we have direction on our edges, so it's a little bit trickier to. Any thoughts on how we might find or compute these? We'll think about the undirected, just the connected components.
Search.
So the search ones would be finding a path from one node to another, which is kind of related to this, but not exactly the same. So what would we search for? We just want to know if things are touching, basically. Any thoughts?
Seems like intuitively to me that you want to find places where they're not touching, actually, like find the divisions between groups.
Yeah, but searching for those are kind of hard, right? So what if we assume that nothing is connected to anything? So if there's no edges, what are the connected components? Each node is its own connected component. So maybe let's start there. So say every single node is its own connected component. Okay. Probably that's not true. So how do we know that that's not true? There's edges, right? So if I see an edge, what does that mean? So what should I do to the connected components for those nodes? So let's say I have a graph that looks like this. And to start out with, I have connected components for A, B, C, and D. So to start out, I assume I have 4 connected components. Each node is separate. And then how do I, this is obviously wrong. How do I correct it? Yeah, so I just look, when I see an edge, I just join them. So, oh, A and B have an edge between them. So I'm going to merge these two. Oh, B and C have an edge. I'm going to merge the components they're in. And I can just do this until I look at all the edges. So, this is how you can compute these connected components, right? You just start with everything separate, and then you just merge things until you run out of ways to combine them. Right. There's a really clever data structure for keeping track of these merges. It's a tree-like data structure, except that it is essentially flat. And instead of storing pointers to your children, children only store a pointer to their parent. It's a really efficient way of doing this. So it's a pretty interesting data structure called a union find. Okay. So these are connected components. All right. You can imagine, right? You want to know basically how many sort of subgroups you have. Right. This is a very discrete thing, right? If I have a graph with like weighted edges, maybe I have one like tiny link between 2 big groups, right? So in that case, my number of connected components probably doesn't necessarily tell me about the connectivity between things. So it's kind of a coarse measure, but it's still pretty useful. Questions about connected components? All right. Yeah.
How do you determine when to connect a component?
So I just basically loop through all the edges, and I say connect the component for this one and the component for this one. So join the component for this one and the component for that one.
There's no like specific specification as to why you would connect C to D.
There's no edge, so I wouldn't.
Oh,
So I just loop through
iterate
edges.
through everything.
Yep. Yeah.
Describe again why this is more valuable than just having a raw representation. Like
The connected components. So if I have these, right, I might do some analysis on A, B, and C separately, right? Because I know they're connected and D isn't. The number of connected components is often a useful thing, just to as like a very first course analysis. Like, okay, well, I'm split into 10 pieces. This can be useful to know. So this is just telling you about the sort of course level connectivity of your data set. So this is a kind of a graph property. In terms of computing this, does either one of these representations seem like a big advantage over the other? And so what we're doing with the graph is basically looping through edges, right? Can I loop through edges with either of these pretty easily? I'd say so, right? So I either like have my list of nodes. For each node, I go through each edge, or here I just go through the entries in my matrix. So either one of these would be a fine representation of that. Okay. Yeah.
How do you make sure that you, like with the different groups, make sure that you loop through all of the nodes? So if you're looking at A, B, and C, obviously you have first, you make sure you're also.
So I would want to have a list of the nodes somewhere. So somehow you have to be able to reach all the nodes. So probably the simplest thing would just be to have a vector of nodes. All right, so the next property we'll look at is another topological thing, but it is, instead of looking at the whole graph, we're going to look at a single node. And that's called the degree of a node. And the degree is basically the number of edges that are connected to that node. If we are dealing with a directed graph, we can talk about the in degree or the out degree. Okay. Yeah, so that's the degree. It is a local property. If I wanted to know, something about the whole graph based on the degree, right? What type of, how might I sort of aggregate that information over the whole graph? What are some sort of graph-wide degree things I might be interested in? Average, min, max, median. Right? These are kind of more graph-wide properties. Right? If I'm working for an airline and I want to do flight scheduling or analysis or something, right? If I want to find probably the busiest airport, right? What's that one going to be? It's going to be the max degree. Right? What should I hope the min degree is if I'm an airline? 1 probably, and hopefully at least all of the airports can fly somewhere. That's the degree. If I wanted to know, so here the degree of a node is pretty easy. It's just the length of my neighbor's vector. How would I compute the degree in a matrix representation? So I'd want to count the number of non-zero entries in a row or column. If I'm storing like the compressed version, that could be pretty fast. If I'm uncompressed, right, it might take a while. I have to loop through the whole matrix, but it should be that's like the most cache friendly. Hopefully, if I laid things out right, that's going to be super cache friendly. I'm just going to go read a bunch of integers in order. Okay. So that's the degree. Again, that's a local property of a node. But we can look at the summaries of the graph by looking at some of the statistics of the degrees. The next one we'll talk about is sort of a mix between the two. This is a per node property, but it depends on the whole graph. Okay. And this one's a little bit weird. It has a strange name. This is called the betweenness centrality. Okay. And we compute it in basically a two-step process. Okay, so the first thing we do is we compute shortest paths from all nodes to all other nodes. Okay. And then the betweenness centrality of a node is basically the number of those shortest paths that contain n over the number of paths. Okay. So this is kind of measuring how much of a choke point this particular node is. Okay. So if I just take the shortest path, from anywhere to anywhere, how many of them have to go through this node? So if I have this graph, what's the betweenness centrality of that point going to be? 1, right? Every single shortest path goes through there. And the betweenness centrality of these is going to be very small. Most paths don't go through there. Okay. So again, this is kind of a coarse thing, right? If I have a graph that looks like this, right? Betweenness centrality is kind of going to be split between those two nodes, right? So if I looked at one kind of independently from the other, it might not be obvious that, oh, these are really like central nodes. So again, this can be kind of a coarse thing, but it can be pretty illuminating. Okay. And so this is kind of a weird hybrid, right? We have to look at the whole graph to get the shortest paths, but it's a property of a single node that kind of depends on that. This one, expensive to compute or cheap to compute? Expensive, right? We have to compute all pairs shortest paths over the whole graph. Right? So that's going to be an expensive thing. Okay. So that's betweenness centrality, kind of a weird one. The next one is also pretty weird, but you all use it every day, and the world is a much better place for it existing. And this is called the Pagerank. So who's heard of Pagerank before? Do you know what it is?
I know that Google uses it.
Pagerank is the Google algorithm. Okay. If you Google like the Google paper, the paper is Pagerank. And it is a way they came up with for analyzing a graph of the internet, or the graph of the internet. Okay. So Pagerank is basically so Pagerank basically, we imagine that we have a random internet surfer. Okay. And the random internet surfer starts at a random page on the internet and clicks links randomly forever. Okay. And Pagerank tells us the probability of him ending up on a particular page at the end of time. Okay. So we have random surfer. Clicks links randomly. And This tells us the PR of n is basically probability of our random surfer ending up at n. So what is this going to tell us? Like we can do this thing, we can compute it, and like what information do we expect to gain from this?
Sites, like specific sites.
Yeah, so which sites are sort of easier to get to? And the insight from the Google guys was the more linked to a site is, the more important it is, the more relevant it probably is. That was probably true in 1997 or 8 or whatever. Probably less true now, but at the time it was a pretty clever insight. And so the pages that are easier to get to, because more people link to them, are going to be more important. So you can weight these. So clicking links randomly doesn't have to be uniformly at random. So one of the things Google did is they weighted the chances of clicking a link based on, is it a heading, like is it a big link? Is it a little link? Where does it appear on the page? That kind of stuff. So you can affect you can change how you choose randomly between the links, and that's the PageRank. So for PageRank, the matrix operation or matrix representation is the way to go, because to actually compute this, we are just doing a matrix operation. And it's actually kind of amazing how it works. So we start with a vector, which could be random, or it could be like the number of pages in the internet, just 1 divided by the number of pages in the internet everywhere. We just want a vector with length 1. That just says kind of where we start. And then basically, so x is like the probabilities of being on each page. And then to do this, actually, all we have to do is take x equals matrix times x a bunch of times. And after a few iterations of this, this actually converges to the correct probability from here. So this is a linear algebra thing. We're finding an eigenvector of our matrix, all we have to do is just multiply a vector by the matrix a bunch of times, and this gives us the PageRank. So this gives us sort of a relative importance of the various nodes in the graph, right? How do we get to the various nodes? Is this more of a directed graph thing or an undirected graph thing? Directed. So for the internet, would it be a directed thing or undirected thing? Are links mutual? Or do they have to be mutual? They're probably not mutual. So this also works. This works well for undirected graphs as well. Right. Okay, so PageRank is kind of a abstract sort of thing, but in practice, it's a very useful analysis to do in graphs. And then the last one we'll talk about is called a clique or a click. I think computer scientists usually say clique. A clique is a fully connected part of a graph. And fully connected just means each node is connected to each other node. Okay, so if I had a 3, let me draw a 3 clique. So that's an example of a 3 clique. I have 3 nodes that are all connected. Here's a 4 one. Right, so I have 4. All of my nodes are connected. And cliques can tell you, so one thing you might do if you're doing graph like simplification is every time you find a clique, you just like compress it to a single node, right? Especially if you're doing like visualization. Right? So that's the type of operation you might do. Because if you're connected to any of the nodes, it doesn't really matter which one you're connected to. Finding cliques is an NP hard problem, meaning that it's basically exponential in the size of the clique that you're looking for. So not an efficient thing to find exact solutions for, but for small cliques, it's okay. All right, so these are just some of the kind of topological properties we might look at for graphs. So how are they connected? How do we quantify the connectedness of the graphs? Any questions about any of those? All right. So the next thing we'll talk about a little bit is kind of related to the betweenness centrality, which is we're going to talk about searching. Okay. So if I want to find, if I need to find paths in a graph either for, like navigation or understanding the cost between 2 nodes or something like that, or if I want to compute something like betweenness centrality, right, I have to be able to find paths in the graph from one node to another. We'll talk about 4 algorithms for doing that, of sort of increasing complexity and efficiency. So the first one we'll start with is depth first search. Did you talk about that at all? So how does depth first search work? I want to find a path from the source to the target.
Just send into the child nodes before you look at that.
Well, I mean, there's not really anything for me to do at this node except look at my children. Right? If I'm here, like I know how to get here. I don't have to do any searching for here. But yeah, I'm going to search from the, because they're not necessarily children because we don't necessarily have a tree. But so I'll search through the neighbors from here, right? And a DFS, what's the order in which I kind of search stuff?
In order, post order.
So that would be for a tree. So I don't, I probably don't have a tree here. I probably have loops and all sorts of crazy stuff.
You split the neighbors in half or something.
Oh, so the order of the neighbors themselves doesn't really matter. So the general idea here in depth first search is I just go forward until I hit a dead end, right? And then I just back up and go forward as far as I can until I hit a dead end, back up, go forward as far as I can until I back up. I'm just going head first as far as I can until I hit an obstruction. So I write out the some pseudocode. So basically, we're going to keep track of like a set of which nodes I visited. And so I'll start with an empty set. Okay. And when I do DFS, if I am at the node I'm looking for, right? I don't have to do any more searching, right? I'll just return. The path from S to T is just S. That's pretty easy. Otherwise, I just have to look at all my nodes, right? So otherwise, I'm going to mark. I'm going to say I'm going to add S to visited. I've been here now. If I get here again, I don't want to search here again. Okay. And then for each of my neighbors, if I haven't already visited that neighbor, I'm just going to DFS search on that neighbor. So if N is not visited, I'm just going to DFS starting at N. Okay. If I can get to the target from here, then I'm finished. Right? I found a path from here to there, so I'm just going to return a path from here to there. Okay. So if my path existed, then I'll just return. I'm going to add myself to the front of the path. Okay. So I get to here and then go from that child on. And otherwise, if I look at all of the neighbors and I don't find a path, then I can't get to the target from here. So I'll just can't get there. All right. So this is the key part of DFS. This recursive call as I'm looking at my children, or as I'm looking at my neighbors, right? I'm just going as fast as I can in whatever direction I can go, right? This is like a very what's the term? Aggressive and spontaneous search algorithm. Right? We're just, oh, I can go that way. Cool, I'm going to go that way. So this is a recursive algorithm as I've written it. So what data structure am I using? What data structure is associated with recursion?
Stack.
A stack. So I'm not writing it out, the compiler is, but here, this means I'm storing on the stack which nodes I have to visit. Okay. So the DFS is the stack search algorithm, right? The nodes that I'm going to look at next are stored on a stack. Okay. So I could write this iteratively with a loop instead of recursion, and I would store the nodes I want to visit on a stack. Okay. Right, so that's DFS. When would DFS be a good algorithm?
Far away.
If I'm far away, maybe. So the good things about it are I'm not going to waste a lot of time, searching around close to me. Yeah. But I hopefully, if I'm far away but I go in the wrong direction with DFS, I'm super hosed. Right? So potentially could be good for far away because I'm not going to explore a lot around the starting point. What other conditions would make DFS good?
Tells you if there is a path. So.
Yeah, so is DFS going to give me the shortest path? No. So if I'm only concerned with if there is a path, DFS is appropriate. If I care about the shortest one, DFS is not going to work. When would it be pretty effective, do we think?
Space matters, like the storage space.
Yeah, storage space. So I'm going to use pretty small storage space. And I'm only storing a stack of where I've been. Like to draw the path. We'll actually look at visualization of all sorts of methods. I could visualize this, but that's not exclusive to DFS. So DFS can work well if there's a lot of different paths to my target. If there's a lot of different ways to get there, it doesn't really matter which order I pick to go. Right? I just pick one and go for it. Right? And I kind of need to, if there's a wrong direction that's going to take me away, that would be pretty bad. And another case where DFS is pretty good is when the branching factor is really high, or when the average node degree is really high. I don't want to have to look at a ton of nodes nearby. Right? DFS, I kind of get going as fast as I can. Right? So when the average node degree is really high, DFS kind of just gets directly out of there without spending a lot of time doing exploration. So that's depth first search. Breadth first search is almost identical in the iterative. So if I had written the iterative version, I could easily tweak it to be a breadth first search. So DFS is the stack search algorithm. BFS is the queue search algorithm. So for breadth first search, I store the nodes I want to explore next in a queue, okay? Which means that I expand and explore nodes basically in order from their distance to the starting point. Okay? So I add all my neighbors to the queue, and then for each neighbor, any new node, I add it to the queue. And so what I actually get, it kind of is like I'm searching out in rings away from where I'm going. Okay. So if I had the iterative version of DFS, everywhere where I used a stack and push and pop, I would use a queue and NQ and DQ. And it would work. It would be the same. So that's breadth first search. I'm searching all of the nodes within one edge, and then all the nodes within 2 edges, 3 edges, and so on. So when would BFS be a good search algorithm? If I care about the shortest path, right? Why is BFS going to give me the shortest path?
If it's using a queue, then it is going by layer by layer.
Yeah, because I'm using a queue, I'm kind of going to go in order of how far away things are from the source, right? So I will get the shortest path, assuming my edges are unweighted. Right? I will have the fewest number of edges to go. Okay? So that's a nice property of it. When else would I want to use BFS? If I think I'm going to have to go 10 links away, is BFS a good, or 100 or 1,000 links away? Probably not going to be great. It's I'm going to have to explore all the nodes that are within that distance, right? If my average degree is really high, I'm going to explore tons of extra stuff that I don't need to. Right? So BFS is good for when I want to do things that are nearby, or I want to find stuff that's nearby. So let's say my my graph is Facebook's graph, and I'm trying to find somebody that I think is a friend of a friend of a friend, right? Is DFS going to work very well? No, right? Depth first search, I'm going to just go off in a crazy direction, right? And I'm going to keep finding random people that are further and further and further away from my social circle, probably. Right? A BFS, right? I'm going to find all my friends, and then all my friends' friends, and all my friends' friends' friends. Right? And if they're close, then that'll be the way to do it. Right. Cool. I think we'll save the other search algorithms for tomorrow. So we'll talk about what happens when we have weights in the graph, and also what happens when we know a little bit more than just what the graph is telling us. So we'll talk about Dijkstra's algorithm, which sounds like you've seen a little bit, and then we're going to talk about the best search algorithm, which is called A star, and it is actually the best, provably. And it's a pretty clever algorithm. So we'll save those for tomorrow. Today we'll just look at a little bit of code to play with some graphs, and yeah, a library, a popular Python library to deal with this stuff. The library we're going to play with is called Network X, and it's just a pretty standard graph library in Python. It's got a lot of the stuff we've been talking about kind of built in. Yeah, we'll go ahead and play with that. So to play along, you'll have to pip install Network X. So here's an example of how we could create a graph. So we have, start with a graph. We add nodes, we can add edges, and then we can, some of the data we can get out of this are just the nodes or the edges of the graph. So our nodes are, in this case, string data, and our edges are these tuple pairs of the two edges. If we add an edge to a node that didn't exist, Network X will add a new node for us. So this guy, Hans Peter, wasn't in the graph before, and is added when we connect him to other people. So it's kind of handy. We can, the nodes are objects, so we can put others, we can add basically other fields to them, kind of handy. So now we see that our nodes, instead of just being the strings, are now objects that have other stuff. So I guess maybe dictionary is the better term, like JavaScript, like objects like you would get in JavaScript. Cool. You can access nodes by name. Okay. also draw graphs using Network X. We'll look at better ways of drawing graphs in the next week or so. This is the method, one of the methods we can use to draw a graph. The spring refers to how they decide where to put the nodes. This is, the nodes themselves say nothing about position information, right? So one of the biggest challenges in drawing graphs is deciding where to put the nodes. And this is an example of what's called a force-directed layout. So they basically put springs between all the nodes, and then they run physics, and they get positions out. So that's what the spring means. So this is an example of the graph. So we had 5 nodes. We had this kind of connected region, and one guy hanging off the end here. We can also draw labels. So, so we can put names on here. A very unfortunate thing about these force-directed layouts, like using springs, is that each time you do it, you generally tend to get a different answer. So you can see this is that we drew the graph twice, and we got 2 totally different layouts. And so that's an unfortunate property of these particular graph layouts. We can also use different layouts. So here's a shell layout where we put stuff around the edge of a circle, and so that will give us a more consistent layout. We'll talk about graph visualization later on, but just a couple of examples of what that looks like. All right, so now we can look at some of the information about it. So we have the info function, which just tells us nodes, edges, average degree. We can get the degrees of each node. And another kind of cool thing, we can scale the nodes easily when we draw based on whatever attributes we want. So here we can scale the nodes by, in this case we'll scale it by degree. So when we draw it with scale degree, we see that Wolfgang is smaller because he's less connected, and the more connected nodes are bigger than the smaller ones. So again, that can help us visually make the highly connected nodes pop by making them bigger. Right. Might also be useful to look at a histogram of node degree. In this case, it's not super interesting, and it looks like the scale here is kind of not that good to look at, but for a bigger graph, this would be a useful thing to look at. It tells you, okay, are there a few nodes that are really important and everybody else is kind of periphery, or are there, are most of the nodes kind of similarly connected? That can give you a good intuition for what the graph looks like. Okay. We can also load, so we saw up here how to explicitly create a graph in Network X. We're very rarely going to do that. Much more often, we're going to input a graph data from somewhere else. And so this is a particular graph layout. So this is called GML. Right. I don't know, not all that interesting, but so we can use a read GML file. So this particular file we're looking at is the graph representation of Les Miserables. No, I don't know if it's the book or the musical. Hopefully they're pretty similar. But the edges are weighted by the number of times that characters speak with each other. So there's an edge if two characters talk, and the weights are higher if they talk a lot. So here are the nodes, which are the characters. So we have all the characters in here. I'm gonna find one that I recognize. Oh, Valjean, Cassette. So we have all these characters. Look at the info. Looks like there's 77 characters in Les Mis. A lot of edges. Average degree 6, 7. So each character talks to 6 or 7 other characters on average. And if we draw this out with the spring layout, you'll see that it's like a terrible mess. A cool thing about the spring layout is that it does group regions that are highly connected together. So you see like this group of characters, I guess, talks to each other a lot. This particular type of visualization is called a node link diagram, where we just draw the nodes and edges, and you can see it gets cluttered really fast. So we'll talk more about, okay, what do we do about this? But yeah, this is what our graph looks like. We have all these people that only talk to one person. Napoleon over here. All right. So here's the graph. The next thing we'll look at is some of the connectedness measures. So we'll draw the graphs kind of weighted with the nodes size based on how connected they are for a couple different ways of measuring that. Okay. So to draw the graph, we will scale the nodes, or these are going to be the node sizes, and then we'll just do a spring layout again. So we'll start by doing degree, which if we look at the degrees, it's like Valjean, who's the Hugh Jackman character, right? He talks with everybody. Who's the actor? Russell Crowe, the Russell Crowe character, talks to way fewer people. Sacha Baron Cohen's not even in here, I don't think. All right, so these are the degrees. The top people are driving the plot. And if we draw the graph based on degree, again, this is not easy to see. But we see Valjean is kind of in the middle and is the highest degree. All the other people are kind of ancillary. So that's based on the degree. If we look at betweenness centrality, right, this is like if you're going to play a game of telephone between the characters, who are going to be the kind of the people that are important. So here's a demo graph. So if we look at this simple one, C has very high betweenness centrality because most of the paths go through it. B is slightly lower because it's not involved in any of the paths of this region. We look at it for Les Mis. Again, NetworkX has a method for doing that. If we looked at all of the betweenness centralities and added them up, what should we get? Should be 1, right? Because each one is the fraction of all the paths. So should get 1 total. So Valjean is a very important character in terms of connectedness, and that's quite obvious if we draw the graph this way. So we can see kind of like there's like a few sort of gatekeepers in here that have relatively high between centrality. Okay, next thing we'll look at is PageRank. So if we have a directed graph, so here we have ABCD, a few edges, and we look at the PageRank. We can see basically a random surfer is pretty likely to end up at A or D, and will never end up at B. And if you look at the edges in this particular graph, you'll see that none of the edges go to B. So if I click around randomly forever, I'm not going to end up at B because there's no way to get there. And so there's edges that get me to A and to D, fewer that get me to C. So that's what this PageRank tells me. If I look at the PageRank of Les Mis, sorted, it's like if you randomly talked with characters, eventually you'd end up talking with the main character. Right? So these, all of the connectedness measures we're looking at seem to be pretty consistent about how important he is. The top two I don't think have changed in any of these. And the top 10 look pretty consistent as well. So these are all, for this data set, all of these connectedness measures are kind of telling us similar things. But if we scale it based on PageRank, again, hard to track these between figures because things get laid out differently. But again, we see Valjean in the middle and everybody else kind of spread out. So let's look at histograms of all these various measures. So histogram of degrees. So it looks like for Les Mis, most people don't get out that much. They talk to a few people, and then we have a couple of like heavy hitters over here. But most people are not talking to all that many other folks. In terms of centrality, that's even more stark, right? Like, these are all the characters we could get rid of and it wouldn't be that big of a deal. Right? And in terms of PageRank, spread out a little bit more. So, if you kind of randomly talk to people, there's a few more people in here that you might end up talking to at eternity. So, so for all these, relatively consistent in terms of what they show, but not exactly the same information. This is a pretty well-connected graph. Let's see what happens if we take out Valjean. So we're going to remove him from our graph, see what we get. So we'll look at betweenness centrality afterward. So Javert jumps up. So he was kind of low before, and he jumped up to the top spot, right? Because before the shortest paths all went through Valjean. Now more of them go through Javert. So this is kind of a weird thing, right? The ordering of this is maybe a little bit misleading because the almost shortest path or the next shortest path gets no recognition. So if we draw this now we see that we actually have a handful of connected components, right? So we have 1, 2, 3, 4, 5, 6 connected components, right? These people only were connected to everybody else through Valjean. And so now we've split things up. And we can see through the number of connected components that we're up to 7, and before we only had a single one. Which kind of makes sense, right? So if you're writing a novel or something and can model your interactions as a graph, if you have more than one connected component, right, that means you have part of your story is completely isolated from the rest, right? That's probably not what you want. You probably want to connect these things. So seems like removing Hugh Jackman would not have been a good editorial decision. Right. So yeah, those are kind of the various connectedness measures, and we get a sense for you know, the relationships between the various nodes, and which ones are more important, and kind of a sense for the overall connectivity of the rest. Okay. Okay. So I'll look a little bit about searching again. So we talked about breadth first search, which gets us shortest paths. So I can use the network X shortest path function to get between these two characters, and it gives me, you know, all the nodes I have to go through on the way to get there. Cool. Or between two other characters, so this one's a little bit longer. Okay, so the BFS, the shortest path, is only counting the number of edges, right? So if there are weights between them, so some edges are either cheaper or more expensive to use than others, then we want to use Dijkstra's algorithm. So we'll talk a little more on Dijkstra later. Here's all our edges. The important thing here is that there are weights along here, which is the number of scenes they're in together, the number of times they talk or whatever. And so, like, these two seem to talk a lot. I guess the kids talk a little bit. So to take the weights into account, we can use the Dijkstra path. I think for this one, we get the same answer, I think. These were the same people we had before. Yeah, I think that path was unchanged. But some of the other paths might be different. Right, so this one, I believe, has more links in it, but a lower total weight. For this one, probably, so we would probably want to adjust the weights for these sorts of paths. Right? As we've set it up, how are we determining the shortest paths? Yeah, who like interacts least? So we're like trying to find a path of like almost strangers to get there. Probably what we want to do is our weight should be like 1 over the number of people that we, 1 over the number of times they talk or something, right? So you get like, you know, the most like interactive links are included. But if we look at the path costs, the weighted paths again are longer but have shorter weights, have lower weights. And I'll just give you a preview of tomorrow. The A-star algorithm is useful when we have a little bit of extra information beyond just the graph, which is we can estimate the distance between two nodes without looking at the graph to get there. Okay? So for example, if you're trying to drive through Salt Lake City, you can estimate the distance between where you are and you want to go by just like the crow flies distance. Right? And knowing that can help guide you in the right place, right? So BFS is gonna, if I try to use BFS to route my car, it's gonna search the wrong direction, right? That's not helpful, right? If I add the extra information, like, hey, I actually only want to search, you know, in the direction I'm going, I can look at a lot fewer nodes in the graph. So that's how A-star works, and we'll do that yesterday. So here's a little visualization of what it looks like. So BFS looks kind of like a circle growing. A-star looks more like a teardrop that kind of, or like an ellipse that kind of goes there. So let's start over. So it's just going as fast as it can towards G, or towards the green node. It doesn't, the heuristic, the estimate of how far away it is, doesn't know about the wall that's there. And then once it finds the wall, it looks kind of more like breadth first search. But breadth first search would have expanded a whole circle. We can't use A star on Les Mis, unfortunately. Why not?
How do we know what direction?
Yeah, we have no way of estimating distance. So we have no extra information. Extra is the best we can do. All right. So that's a kind of a quick intro to some of the graph analysis we can do. We'll look more at graph search and graph visualization as we go forward, and we'll keep playing with graphs for the next couple weeks. Any questions? All right. See you tomorrow.